Welcome to week 3. So we're going to start this week off by looking at a new kind of function and how to find their derivatives. So just to recap, although we've done this many times so far, we know that a function is a set of inputs and a set of outputs and a rule that takes each input to exactly one output. So for example, we might have a set of inputs like 1, 2, 3 and a set of outputs like 5, 6, 7. And the rule says you can take 1 to 5. You could also, if you like, take 2 to 5 and maybe 3 to 7. The only thing that you're not allowed to do is to take one particular input, for example, 3 to 2 different outputs. And one of the key things about writing things as a function is that we can write them in the form y is equal to some function of x, where on the right-hand side here we have only terms involving x, where x is our input. So our function basically takes all its inputs in and spits out our output y. Okay, I know you're wondering, why are you telling me this again? It's going to become clearer in a moment. After we talked about functions for a while, we started thinking about finding their derivatives. So remember that a function, if we graph it, tends to look something like this. And because we're using them to model things, we often want to know about the rate of change. And it turns out that if you want to find the rate of change at some particular x value a, what you need to do is you need to find the slope of the tangent at a. So our derivative, which is df by dx, is the slope of tangent at x is equal to a. And one of the things to notice here is that when I tell you that I'm thinking about my function f of x, and I'm thinking about it when x is equal to a, that tells me immediately which y value, because for each x value you only have one y value. So you know if I'm saying x is equal to a, then the y value must be f at a. Okay. So this is great, and it's very useful for many models. But what happens if we have a model where we need to use a curve like one of these? So you can imagine if you've got circular motion, then your motion is described by something like this beautiful circle over here. And the first thing that you're going to do when you look at that is go, well, that's not a function. Because remember, we can use the vertical line test. And there's a vertical line, it cuts our curve in two places, so this is not a function. The same thing happens with this beautiful curve over here, which is called a lemniscate. Okay, the situation is actually even worse, because if I draw a vertical line here, it now cuts my curve at 3 places. So these are definitely not functions, but they might be curves which adequately describe a particular phenomenon that you are looking at. And so you want to be able to study them. And in particular, you'd like to be able to think about their derivatives or their rates of change at particular points. And if one feels intuitively we should be able to do this, because I can certainly draw tangent lines to my circle. So there's a tangent line at a point, so I should be able to find the slope. And therefore there is a derivative associated with my circle at that point. And the same thing with my lemniscate. I could draw a tangent line here, or I could even do a crazy vertical tangent line there. And that's telling me something important about the lemniscate. But at the moment, we don't have a way of finding those derivatives. So that's really what this course is about. This part is about. So what do we call curves like the circle and the lemniscate? Well, we call them implicit functions. And I hope at this point you're going, but Claire, they're not functions. And the reason we call them implicit functions is, well, they are kind of functions in the sense that you could break them up into functions, which when you use all the functions together, give you the curve. What do I mean? We could divide up our circle into the top bit. So that's a function. So that would be y is equal to the square root of 4 minus x squared. And we could take the bottom and we could describe that as y is equal to minus 4 minus x squared. And so we've split our circle, which is not a function, into two things which are functions. So that's why we kind of get away with saying that they're functions. So the other word here is implicit. Now, if you think about just the general meaning of the word implicit, it means suggested though not directly expressed. So if someone kind of asks you implicitly to do something, they're not going to say, please do this thing. They kind of imply that they would like you to do that thing. And in a mathematical context, an implicit curve is one in which the dependent variable, so think your y variable, is not explicitly expressed in terms of the independent variable. So in plain English, what that means is you can't write the curve in the form y is equal to some function of x, where this thing has only x, whatever crazy thing it is. So when you've got an implicit function, you're going to find, as you can see with our circle and our lemnis gate, we can't rewrite this as y is equal to something that only contains x. Because if we tried to do that, we'd have to have y is equal to, well, we've had to take the square root, so we've really got to have plus or minus 4 minus x squared. And this is a problem here, because that means we're not a function. So we can't do this. And similarly, if you tried to solve this for y, you'd reach the same problem. You can't write it in the form y is equal to some function of x. Okay, so here we have these bunnies are called implicit functions. And what we'd like to think about is how could we calculate the derivatives? So we want to be able to find tangents to things that we can't write in the form y is equal to blah, blah, blah. And if you think about why at the moment we can't do that, it's because when we have something like y is equal to e to the x plus sine of x, when we take the derivative, we say, okay, well, dy by dx is equal to e to the x. So we take the derivative on one side and just do the derivative on the other side. But what do we do if we have something written like this? Okay, well, let's do a kind of preliminary exercise that's going to lead us to where we need to go. So here we've got a bunch of problems where we've got some function f. I don't know what it is. We just know that it's differentiable. So remember that saying dy dx of f of x is the same as just writing f prime of x. So if you want to tell someone that you want the derivative of f, you just write f prime of x. So what I'd like you to do is just take a moment and figure out what these 5 derivatives all are. So just take a moment and think about what they'll look like. And be particularly careful when you're dealing with things like, for example, that term in C, and notice that this is an x squared here. So see what you can do, and then come back and we'll work through them. Okay, so I hope you did give that a try. Let's have a look. So if we look at A, what we want to do is we want to take the derivative, so that's what this d by dx says, of x squared plus f of x. Well, we analyze our function in the outer, and we see that this is a sum, so we know that our solution is going to be some term plus another term. And the first term is going to be the derivative of x squared, which is 2x. Then we're going to add that, and we want the derivative of f of x, but we don't know what that is, so we just put in the notation that says whatever the derivative of f of x is, which is f prime of x. Okay, so that was super easy. Let's have a look at B. So now we're taking the derivative of x squared times f of x. And we look at this and we say, okay, this is a product. It's an x squared times an f. So I need to have the product rule, so I'm going to have 2 terms added together. The first term, I'm going to take the derivative of the first bit of my product. So I'm going to say 2x, and I'm just going to multiply it by the second bit. And then I'm going to say, I'm going to write down my first bit of the product and take the derivative of the second bit. And again, don't know what that derivative is explicitly, but I'm just going to write down f prime of x. Okay, straightforward. So if we move on to c, now let's have a look. We've got d by dx of c plus x plus f of x squared. So this again is a sum. So we're going to have the derivative of the first term. Derivative of a constant is 1. Derivative of x. Sorry, the derivative of a constant is not 1. I hope you caught that. Derivative of constant is 0, because if you think about a constant function that has a 0 slope, if you think about the function y equals x, that has a slope of 1. Okay, so we have a 0 plus 1 plus, and now we need the derivative of this term. And here we're actually thinking chain rule, because we've got a something squared. So a function that's not just x, we've got an f of x squared. So our chain rule tells us that this should be 2 times f of x times the derivative of the thing that's squared, which in this case is f prime of x. So if that felt a bit weird, go and revise the chain rule from last week. Okay, how about d? Now d says take the derivative of f of x squared. So again, we've got a chain rule, because we want to take the derivative of something that contains a function inside it. So we use the chain rule. Chain rule says, okay, well, that's going to be the derivative of f with respect to x squared times the derivative of x squared, because that's the inside function. So that's times 2x. Alrighty. So I'm going to leave E for you to do, and I will put the solution in the final version of these notes. Okay, so this was slightly different differentiation, and it leads us to a cunning way of finding the derivatives for our implicit functions. So remember, we're looking at something like x squared plus y squared equals 4. And what we're going to do is we're going to view y as an implicit function of x. So we're really thinking of y as some f of x. We don't know what it is, but we just know that it is a function of x. And this gives us a way of differentiating our implicit functions, because what we can do is we can differentiate both sides of that equation. So if I've got x squared plus y squared is equal to 4, now I'm going to differentiate both sides. So I'm going to say I want d by dx of x squared plus y squared, and that has to be equal to the derivative of 4. And remembering that we're thinking of this really as some f of x all squared, we've really dealt with this before. We know how to go about this. So we're going to take the derivative of x squared, which is just 2x. And now we're going to take the derivative of some unknown function, which is squared. So that's going to give us 2 times that unknown function. And then we need the derivative of that function. So I'm keeping it in the f notation just to emphasize the fact that we're thinking that y is equal to some f of x. And then finally we need the derivative of 4. As we just figured out, the derivative of a constant is 0. And so finally, going back to the variables that we were using at the beginning, we've got that 2x plus 2y times dy by dx is equal to 0. Now we're not quite done, because usually when we have derivatives, we write them as a function, if you like. So we would write dy by dx is equal to stuff. So let's just rearrange this and we'll be done. So I'm taking my 2x over to the right-hand side. So I've got 2y dy by dx is equal to minus 2x. And I'm just going to divide through by 2y. So I've got dy by dx is equal to minus x over y. Okay, so this doesn't look quite like we're used to for derivatives because there's a y sitting on the right-hand side and we're used to just having functions of x. So this derivative is also an implicit function of x, which is probably not unexpected. We're taking the derivative of an implicit function. It's probably going to end up being an implicit function too. So we've found that our derivative depends on x and y, and although we might not realize it right at the moment, it actually makes sense given what we know about tangents of a circle. So to see that, let's head over and have a look at GeoGebra. So here I've got my circle, and I've drawn the tangent at the point 1.35, 1.48. And GeoGebra very kindly will calculate the slope of that tangent as minus 0.91. And notice that if you plug the x and y values, 1.35 and 1.48, into what we found for our derivative, which was minus x over y, you get minus 0.91. If we move this point a little bit, so we're moving it all the way up to the top, well, that's good news because you can see that the derivative, the slope of the derivative we calculate, or the value of the derivative that we calculate, which is the slope of a tangent, is 0. If we bring our point round a little bit more, now we've got a tangent that is sloping upwards, so it's become positive, and again the slope and what we would calculate are the same. You might wonder what happens if I bring my tangent all the way down to minus 2,0. Well, there my tangent goes vertical, so we would hope that the calculation gives us something that says I can't calculate that, and it does. Because if you think about what we're trying to do, we're saying minus 2 over 0. We can't divide by 0, so it's undefined. Okay, so it seems like what we've done is find a particularly handy way of finding these tangents for things that are not functions. Looking at this a little bit further, you can see why we have to have an x and a y in our formula for the derivative. Because we can't just say, okay, well, find the derivative when x is equal to minus 1, because when x is equal to minus 1, on this particular curve, you might be having a positive y value, but you might also be having a negative y value. And those have two different derivatives and two different slopes, so you have to tell the function which one you want, which y is the y that you want linked to that particular x. Okay, so let's pull that into our notes. Here we go. Okay. So a couple of points to ponder, as it were. You might have seen this notation before. When we want to say evaluate the derivative at a particular point, we sometimes just use this notation here, which says evaluate the derivative when x is equal to a. But you might also have seen this notation that we have here, which says evaluate the derivative at the point ab. Now, we can use this notation when we have functions that we've been dealing with before, but obviously we can't use it when we're dealing with implicit functions, because remember we've said we have to specify the y as well as the x. So when you're dealing with implicit functions and their derivatives, you will use this notation over here. So if you think about what we just found for our circle, if we want to evaluate the derivative at, for example, let's think about the point 0, 1, or maybe rather 0, 2, what do we get? Well, we substitute in x equals 0, y equals 2, into, remember our derivative is minus x over y, and that's going to give us minus 0 over 2, which is going to give us 0, which is what we would expect, because remember that's right at the top of the circle where this tangent line is flat. Okay, so that's just finding out a little bit of notation there, so just be aware of that. And linked to that is that there's notation that looks very similar, but it really is quite different. So the two things we want to think about are d by dx and dy by dx. And these are fundamentally different. So d by dx is an instruction. It says take the derivative of whatever comes after this. So in this case over here, this says take the derivative of x squared plus y squared. On the other hand, so let's write that, that's an instruction. And I'm going to put this in a different color. If we think about dy by dx, that is saying this thing is the derivative of y with respect to x. So taking the derivative has already been done. So if we look at this equation over here, this says take the derivative of y with respect to x and multiply that thing by x squared plus y squared. So over here, this would read as take derivative of x squared plus y squared. This thing over here says multiply x squared plus y squared by the derivative of y with respect to x. Okay, so just be picky about your notation. If you want to write down that I'm about to take the derivative, I'm going to take the derivative of this thing, here is the notation that you use. But if you're referring to a derivative that you've taken, then you use that notation. All right. So after all that talking, here's something for you to try. So please find an equation for dy by dx if we have the implicit function x cubed plus y squared minus 2xy is equal to 2. And see if you can write it in the form dy by dx is equal to something that includes x's and y's. Okay, so go and have a look at that and come back when you're done. Okay, so I hope you did it. So we have our equation x cubed plus y squared minus 2xy is equal to 2. And we want to take the derivative on both sides. So I'm saying take the derivative of that and take the derivative of that. All right, here we go. Derivative of x cubed is 3x squared. Derivative, now remember, when we're doing this sort of implicit differentiation, that's what this is called, we're thinking of y as a function of x. It's just a function that we don't know explicitly what it is. So what we've got to have here is 2y times the derivative of y, which I should write as dy by dx. So that was a chain rule that I used here. The next term that I look at, I've got a minus 2 times x times y. So I'm thinking of this as a product and remembering that y is a function of x. So I'm going to have a minus 2. I'm just taking that out because my constant multiplies, and now I'm going to do the product rule on my x times y. So derivative of x is just 1 times y plus x times derivative of y, and that's going to be 1 times dy by dx. Again, it's a chain rule. Not quite done because we need to do the right-hand side, so now I need the derivative of 2, which is just 0. Sure, okay. So let's just multiply this all out and see what we've got. We've got a 3x squared plus a 2y dy by dx minus 2y minus 2x dy by dx equals 0. And we want to end up in a form like so, where we just have our dy by dx on one side and the x's and y's on the other. So we need to do a little bit of tidying up. All right, so I'm going to take my 3x squared and my minus 2y over to the right-hand side. So I've got 2y dy by dx minus 2x dy by dx is equal to, and I'm going to have a 2y minus 3x squared. Now remember that our dy by dx, this is really just a function, so I can take this out. I can factorize. So I've got dy by dx times 2y minus 2x is 2y minus 3x squared. And now I'm just going to divide through by 2y minus 2x. So I've got dy by dx is equal to 2y minus 3x squared all over 2y minus 2x. Okay. So there's a little bit more involved when we're taking the derivatives of implicit functions, because usually once we've just taken the derivatives and tidied things up, we're done. But when we've got an implicit function, there are going to be a few more steps while we reorganize and get it in the form dy by dx equals something that just has x's and y's. So it's just algebra, but it is quite important algebra, because once we have the derivative in this form, we can start to think about what it must look like. So for example, we can think about for what values is this derivative going to be 0? So when is the tangent going to be flat? For what values of this derivative is the function going to have a vertical tangent? Things like that. So having it in this form is kind of important. So to give a bit more practice, here you go. So we've got another equation. It's x is equal to y to the 5 minus 5y cubed plus 4y. And you can check for yourself that you can't write that in the form y is equal to some function of x. It's definitely implicit. And you can see that as soon as you look at the graph, which we have down below. So what I'd like you to do is spend a bit of time working through these 4 parts. Explain why we can't express y as an explicit function of x. Then do the whole implicit differentiation thing. Then use what you find to find the equation of a tangent to the graph at a particular point, in this case 0, 1. So we haven't really looked at that before, but you know how to find the equations of straight lines if you know their slope and a point on them, so go forth and do that. And then think a little bit in part D about how you would work that. So give that a go and come back and we'll talk about it. So I hope you gave it a try. Let's have a look. So if we think about why we can't write y as an explicit function of x, remember that in order to do that, you need to have a function. That means you have to be able to say, well, this x value maps to this particular y value. But if you have a look at our function over here, for example, if we look at the point x is equal to 1, we've got multiple y values that are all mapping to the same, or all being mapped to by the same x value. So we can't express this in the usual function notation. So if you write that down, we'll say there are some x values that are mapped to multiple y values so this is not a function and cannot be written in the form, y is equal to some function of x. Okay. So now we want to use implicit differentiation to find the derivatives of this crazy function. We've got x is equal to y to the 5 minus 5y cubed plus 4y. And we're going to take the derivative on the left, and we're going to take the derivative on the right. Okay, here we go. So derivative of x with respect to x, pretty straightforward. We know that that's just equal to 1. Now we just have to remember that we're treating y as some implicit function of x. So we don't know what it is, but we do need to include the derivative whenever we take a chain rule. So here I've got y to the 5. So the derivative will be 5y to the 4. And then I need to remember that I've also got to multiply by the derivative of y, because this is really a chain rule. So this is times dy by dx. And let's just make it clear that that's a 3. We do the same thing over here. So I've got minus 5 times the derivative of y cubed. So it's going to be minus 5 times, so this is going to be 3y squared times dy by dx. And then finally, I've got 4 times the derivative of y. All right, let's tidy this up a little bit. So we've got 5y to the 4 dy by dx minus 15y squared dy by dx plus 4 dy by dx. All right, and now we need to do our little bit of work so that we end up with dy by dx on one side and stuff involving x's and y's on the other side. So I'm taking out a common dy by dx and I'm mentally switching sides. So I've got dy by dx is 5y to the 4 minus 15y squared plus 4 is equal to 1. Nice, all we have to do is divide through by my 5y to the 4 term. So we've got 1 over 5y to the 4 minus 15y squared plus 4. And there we go. Okay, so now we have an explicit form, an implicit form for our derivative. Implicit because we've got y's in there. Now we don't have any x's, but that's fine. You don't have to have them. The key point here to note is that we do still have y's. So at any particular x point, I'm still going to have to tell which y I'm thinking about. Okay, so there is my derivative. Let's look at point C. So now we want to find an equation for the tangent line to the graph at the point 0, 1. So if you think about finding a straight line, you need to have, well, you can do this in multiple ways, but ideally if you have the slope and a point on the line, you're good to go. Okay, so want tangent line at 0, 1. Okay, so let's find the slope. Well, we know that the slope is our derivative evaluated at the point that we're interested in. So let's plug in x is equal to 0, y is equal to 1, and that will give us 1 over 5 minus 15 plus 4, which is equal to 1 over minus 10 plus 4, so that's minus 6. So let's just do a quick sanity check. We're looking at the point 0, 1 on our function, and we think that the slope is minus 1, 6. Let's go and have a look at the diagram. So we're looking at the point 0, 1. So we're interested at this point here, and we're looking at the tangent line. And what we want to ask is, does this have the slope minus 1 over 6? Does that make sense? Well, the first thing is, at least it's negative. So this slope is going down. So if our slope is minus something, that makes sense. And 1 over 6, well, that's quite a gentle slope. And if you drew this slightly more accurately, you'd probably be able to calculate by doing change in y over change in x that it is minus 1 over 6. So that looks kind of reasonable. So sanity checking your work is a very sensible thing to be doing. Okay, so we've got the slope. Now we just need to have the equation for the line. So our line has the equation y is equal to mx plus c, and our m is the slope. So this tells us so far we've got our line is minus 1 over 6 times x plus c. So we just need to find c. To do that, we just plug in a point on the line, which we have, a perfectly good one, 0, 1. So we're going to substitute 0, 1 to find c. So we've got 1 is equal to minus 1 over 6 times 0 plus c, so we can conclude that c is equal to 1. And finally, this tells us, therefore, our tangent line at the point 0, 1 has the equation y is equal to minus 1 over 6 plus 1. Whoops, and there's an x in there. Let me make it clear that that's not in the denominator. There we go. Again, a quick sanity check. Did we do something stupid? Because I tend to make really silly errors. So we know that minus 1 over 6 is fine for the slope. Does plus 1 seem to be okay for the y-intercept? If we head back here, yes, it absolutely does, because we know, in fact, that our y-intercept is at y is equal to 1. Okay, so we've finished part C. We've found the equation for our tangent line. And now we just need to deal with part D, which says determine all of the points at which the graph has a vertical tangent line. So what does it mean if something has a vertical tangent line? How can you tell? Well, vertical tangent line, if you think about it, has an infinite or an unknown slope. So slope can't be calculated. So if we think about the derivative that we calculated, we got dy by dx is 1 over, actually let's just copy this bit. So what we're interested in is, when is this thing over here undefined? And obviously it's going to be undefined whenever our denominator is 0. So our derivative is undefined when denominator is 0. So we solve for when the denominator is 0, and that will tell us for which y values our derivative is undefined. Alrighty, so I'm not going to do that. I'm going to put the answer in the final solution, but you should just make sure that you're happy factorizing that and finding which values of y make it equal to 0. Alright, so that was a little bit about implicit functions and implicit differentiation. Coming up next, we're going to head to the other end of the spectrum and talk a little bit about integration, and do a bit of integration recap, and then we're going to be using both of the things, both implicit differentiation and integration, for the final part of this lecture, which is all about differential equations. Okay, so spend some time getting familiar with this, take a break, and then come back for an integration recap.